Assalamu alaikum. Today's section, today's second lecture of category theory. I am going to explain some examples of category. So first of all, the category of set. Okay, denoted by set. So objects of this category is sets. Means X, Y, Z belongs to set category, where X is a set, Y is a set, and Z is a set. So second, set of morphism. Set of morphisms or functions. Functions means form of x comma y is equal to the set of functions from set x to y, okay, whose domain is, let's say, any function f from x to y whose domain is x and codomain is y belongs to this set. Means the category of set. In category of sets, the class of morphism or the object of morphism is the set of functions. Third, by natural composition, if there is a function from x to y and another morphism from y to z is g, so by natural definition of set, there is a composition function g of f from x to y. So for all x belongs to the objects of set category, there exists the identity morphism, means identity function from x to x. Second, we are talking about axioms. So uh, in function, they satisfy the identity law by naturally. If there exists a function f from x to y and identity function, identity y, id on y from y to y, and id on x from x to x. If we compose f with id on x, or if we compose f with id on y, which is equal to f. So second, composition associative law hold according to according to function property. If f is a function from x to y and g is a function from y to z and h is a function from z to w, so we can write f compose h compose g is equal to h of g compose f. So this is the set category of set. Now we are going to another example. So category of groups. Objects are groups. Morphisms. Morphisms are group homomorphisms. Group homomorphisms and composition law hold. Composition exists if there exists a group X and there is a group homomorphism from X to Y, and there is another group homomorphism from Y to Z, which is G. So there is a group homomorphism G of F. We can compose these group homomorphism. So this morphism, group homomorphism from X to Z, okay? And for all group X belongs to the category of groups. So there exists an identity homomorphism from group X to X, okay? Now we are talking about axioms. Identity law. First of all, identity law. Identity law hold if there exists a function group homomorphism from X to Y and identity ID on X group homomorphism from X to X, and there is a identity group homomorphism from Y to Y. So if we compose ID on X with F, or F composed with ID on Y, which is equal to F by the property of group homomorphism. Okay. And associative law also hold in group homomorphisms. So another category of vector spaces, category of vector spaces, or we can say vect category K, whose objects are vector spaces and morphisms are linear transformations, and by default any composable pair we can compose g of f from vector space X to vector space Y. And identity linear transformation ID on X from xk to xk, and composition, and according to linear transformation identity law hold and associative law also hold. So vect k category, there is the objects of vect k category vector spaces, and any two vector spaces there is a morphism which is linear transformation. And linear transformation, if f is a linear transformation from X to Y and G is a linear transformation from Y to Z, so we can compose G of f. So there is a linear transformation G of f from X to Z. Okay. And identity law hold and associative law hold by default. Now we are going to another category. I am going to see group as a category. Any group is a category. Can we check this? Group is a category. So let's say objects. What is objects? What is object in the category group? So choose a dummy object, which is dummy object, which is static. Okay, this is a object in category group. And morphisms, what is morphisms? So we are choosing morphisms in group as a category. So the elements of groups are morphisms. Now I am clearing, and the category of a group, one group, we are we are uh, we are saying this group is a category. So let's say we choose dummy object, and let the elements of group are morphisms. So what is the composition? Means if we say X is an element of group, is a morphism. So one object is here, dummy object. So X is a morphism from dummy object to dummy object. So which is another morphism Y from dummy object Y, another object, another element of group from dummy object to dummy object. Okay. So we can compose. How can we compose X and Y? If we see the picture of group structure, how can we compose X and Y? So how can we compose? We can compose. Yes, we are answer. We have answer. We can compose by using the binary operation. Okay, binary operation. If we use binary operation as a composition, as a composition, so we can compose. Okay, so we have a binary operation as a composition. So we can compose x to y, x binary operation with y from x to from this object, dummy object to dummy object. Okay. So now we are going to explain another thing, axioms. So associative law, how can we associative law? And we know, as we know, associative law, sorry, associative law. So how the associative law hold? So as we know, the definition of group, associative is the property of group between the elements of group. If we take A is a morphism from dummy object to dummy object, and B is a morphism from dummy object to dummy object, and C is a morphism from dummy object to dummy object. So we can write A binary operation with B steric C equal to A steric B steric C according to the property of group. So associative law hold in this category, and for all X for all element, there is a one element dummy object belongs to the object of group category. So there exists a identity. So identity morphism, identity element belongs to group by definition. So which is hold, and identity law also hold. If we compose A compose E or E compose A, we can get A. So this is, yes, group as a category. We can see group as a category whose objects are dummy object, one dummy object. The elements of groups are morphisms, binary operation as a composition law, and associative law hold by default the definition of group and identity. There exists an identity element in group definition. So here identity morphism, because we are choosing the element of group or morphism here. So there exists an identity morphism E from dummy object to dummy object. There is an only one object, dummy object. So there exists an identity morphism, which is identity element, and associative law by default by the definition of group, and identity law hold by the definition of group. So we see group as a category in category theory. Okay, Allah Hafiz.